All right, now we're looking at a different type of improper integral. This is the second video in this topic. The first one went over type 1 improper integrals where the integral, one of the limits was an infinity, right? Where the integral would go from like a to infinity, or from negative infinity to a, or from negative infinity to positive infinity. In this type, instead of having the x values approach infinity, now we have a y value that approaches infinity on the function. Either at one of the endpoints, so like this first example, the integral from a to b, where we apparently have a vertical asymptote at a, and that function is getting close to it, but never quite gets to a, right? Or the right endpoint from a to b, where the vertical asymptote's at b, or where you have some kind of a vertical asymptote in between the two limits of integration, a discontinuity that way. Now the definition in most textbooks will say a discontinuity, and so you might think of other discontinuities too. I will just mention that it's the vertical asymptotes that are the ones that are tricky. If you have a whole, let's say, a removable discontinuity, and you're doing an integral, the whole, a single point, which is what makes it a removable discontinuity, right? Like a single hole doesn't really do anything, right? The area doesn't leak out, so to speak, and so you can still do it the way we're going to with limits. You can integrate from a to c and from c to b, and take the limit as x approaches c, and because the whole is removable, you'll end up getting a finite value. But once you kind of realize that, you can kind of disregard that issue and just go from A to B, right? Or if you have a jump, same kind of deal, right? If you whether you have a point at one end or just a hole at both ends or whatever, if you have a jump, again, the area doesn't leak out through the hole, and you end up looking at this. You kind of break it into two pieces, and you do the one piece before the jump and then the piece after the jump, and it's not that big of a deal. But you could attack it the same way that we're going to attack this third case here. But I'm going to focus more on these vertical asymptotes because they're the ones that are harder to know what's going to happen before you start. So let's start with this first example. Just again, the notation here, how to handle this. Since in this first example, the vertical asymptote is at a, again, we're going to write this as a limit. We're going to write the limit as x approaches a. I'm sorry, I don't want to use x because I have x in my integral, so I'm going to use t, different variable here. The limit as t approaches a, and since we're looking at the, this area under the curve here, let's call this t. T is going to approach a from the right side in this case. So the limit as t approaches a from the right of the integral from, and now we're using t instead of a, from t to b of f of x dx. Okay, so that's kind of how we would define this case. And then same thing here. Ignore the other side of this. We're just going from a to b, so we're in this area here. We're looking for the area under the curve, but again, there's this vertical asymptote, so like goes up infinitely, right? But again, how close is this curve to that vertical asymptote? Like how long does it take for that curve to really get up really high? That's kind of the question. Is this region, does it have a finite area, is the question. And so again, if you kind of draw a line here to give yourself a t, and we're looking at the area from a to t as t approaches b, that's the idea. In this case, since t is to the left of b, t is going to be approaching b from the left, and it's the integral from a to t of f of x dx. And then finally, this one's tough to catch sometimes. If your function has a discontinuity in the middle of this interval, especially a vertical asymptote, right? I showed you a couple other cases with a hole or a jump where it's really not going to matter, right, if that's all it is. But if it's a vertical asymptote and something, y values are approaching infinity or negative infinity in there, then that's where you really have to be careful that you don't miss it. You need to, again, split up this integral from a to c and c to b, and so you can write it that way and then write it as limits, or you can go straight into the limit notation. So we could go from a to t. Oh, you know what? I'm sorry, I should do the limit here first. The limit as t approaches c from the left side, right, for this first part, because t will be over here. And let me call this one t1, just to distinguish between my two t's. The integral from a to t1 of f of x dx plus the limit as t2 approaches c from the right of the integral from t2 to b of f of x dx. Okay, so again, that first limit is really just of that first integral, and that second limit is of that second integral. And you just do them both separately and add them together. And, you know, sometimes, depending on the function, sometimes these could both be finite. When you add them together, then you'll get something finite. And sometimes they'll both be infinite. And it's also possible, depending on how the function is defined, for one to be finite and the other to be infinite. But if either one is infinite, if either side of that has an infinite value, then it's the integral diverges. Even if, kind of like that example I gave in the last video, even if one side approaches negative infinity and the other side approaches positive infinity, and even if they're symmetric about that vertical asymptote, about the point C0, right, to where like it would seem like the areas might cancel out and give you 0, doesn't matter. You have to split it up, and if either one is divergent, then the whole thing is divergent. All right, so let's look at a couple examples. Here we have the limit, we have the integral. It is a limit, but the integral of 1 over the square root of x minus 2 from 2 to 5. And you notice if you plug in 2, we have a vertical asymptote there, right? It approaches, or the denominator is 0. Function's undefined there. But again, we can write this as a limit. The limit as, I'll say t approaches 2, again from the right, because we're looking at values between 2 and 5, so those are all to the right of 2, of the integral from now t to 5 of, and this is x minus 2 to the negative 1/2, right? So I'm just going to write it that way. Now you could do a u substitution here, but if you've done a bunch of these, you know that adding or subtracting a constant directly onto your variable doesn't really change the integration process. You can just kind of bring that, it's really a translation, right, on x, a lateral left-right translation. You just kind of bring it along for the ride here and not worry about it. So let's just keep this in line here. We've got the limit as t approaches 2 from the right of, and again, we're going to do the power rule, right? We're going to add 1 to this power. Negative 1/2 becomes positive 1/2. We're going to divide by the new power, which is 1/2. So when you divide by 1/2, you multiply by the reciprocal, which is 2. And we're going to take that, evaluate it from t to 5. And again, it's the limit of this as t approaches 2 from the right. And so what we get is, when we plug in 5, we're going to get 2 times the square root of 5 minus 2, so square root of 3, minus 2 times the, I'm going to write it as a square root, the square root of t minus 2. And again, this is the limit as t approaches 2 from the right. And since t is approaching 2 from the right, this is a positive value under the square root, but it's approaching 0. And so this is just 2 square roots of 3. So indeed, even though you have this vertical asymptote and this function, the area under this curve on that interval is indeed going to be finite. It has a value 2 radical 3. That's the limit of it. All right, the second one, and again, I encourage you to pause and try it yourself. Okay, so we've got the, I'm sorry, this one's written wrong. I was just looking at this pi over x. I didn't mean to have the pi over x there. That's funny. Sorry if you already tried this one. I'll try to put an edit in there in the video so that hopefully you didn't try it. secant of x dx. I think I just, oh, and there's a dx. I think I was looking at this while I was writing it. Anyhow, makes it a little easier looking, doesn't it? So again, we're gonna have a limit here, right? The issue is when you look at the secant function, secant of x, secant of course is 1 over the cosine of x, and the cosine of 0 is 1, that's fine. But the cosine of pi over 2 is 0. And so 1 over 0, right? This is where the issue is. Pi over 2 is a vertical asymptote on the secant function. So we're going to write this as the limit as t approaches pi over 2. Again, from, this time it's from the left, right? Because we're looking at values between 0 and pi over 2. So as t approaches pi over 2 from the left, of the integral from 0 to t of secant of x dx. Okay, and this is still actually a pretty tough integral, but if you know your integration rules, and this one's, it's a tough one to kind of prove. You have to multiply by a factor of secant of x plus tangent of x on top and bottom, and then go from there. But the rule is this antiderivative is just the natural log of the absolute value of secant of x plus tangent of x. So we still have our limit. And then we've got the natural log of the absolute value of secant of x plus tangent of x, again, from 0 to t. So when we plug in t, we're going to get the, let's take that limit still. We're going to get the natural log of the absolute value of secant of t plus tangent of t minus the natural log of the absolute value of secant of 0, which is 1, plus tangent of 0, which is 0. So we're going to have the natural log of 1. Here, you know what, actually, let me write that in line up here, since it was short the way that I wrote it, and save us another line here. Whoops, use the eraser tool. Okay, and so now, again, that limit is really on this whole thing, although the natural log of 1's a constant, and it's, oh, it's actually 0, isn't it? So it doesn't matter too much. So really we just now are taking this limit as t approaches pi over 2 from the left of this natural log of the secant of t plus tangent of t. And the problem we run into here is that the tangent of t is undefined. It approaches infinity as, as t approaches pi over 2 from the left, right? So we've got the natural log of, well, secant's approaching, well, it's the same issue, right? Both of those have an infinite value, and so they don't exist. This limit is divergent because of that. I'm going to write it this way. Just each of these diverge as you plug in as t approaches pi over 2 from the left. Okay, both of them approach positive infinity. So with that in mind, yeah, this is a divergent one. Notice it's addition too, so you have infinity plus infinity, taking the natural log of that. Yeah. Okay. All right, last one here. This one, the issue is that we have this vertical asymptote in the middle, not exactly in the middle, but somewhere in the midst of this definite integral on that interval. So there's a vertical asymptote at 1, and the integral goes from 0 to 3. So we have to split this up. You have to integrate it from 0 to 1 and from 1 to 3. And again, you can use t in here and put the limit in right away. In either case, the antiderivative here is going to be a natural log, right? It's going to be the natural log of the absolute value of 1. Or sorry, the natural log of the absolute value of x minus 1. That's going to be evaluated from 0 to 1, right? And here, I'll use t at this point. The limit as t approaches 1 from the left for that first integral, right? Plus the limit as t approaches 1 from the right of the natural log of the absolute value of x minus 1 from t to 3. Okay, and I could be using two different t's here, t1 and t2, if I wanted to keep them separate. They are different because this one's a limit as t approaches 1 from the left. This one says t approaches 1 from the right. Because the limits are separate though, and each t is kind of contained within its own limit, you don't necessarily have to do that. Anyhow, in both cases here, when you plug in 0 for x, we're going to have a natural log of a negative value. And then also, while we're at it, when we plug in when we plug in 0, you'll get a negative value, but it's in an absolute value, so that's fine. So we're going to have the natural log of 1, which is 0. But when we plug in 1, right, when we're taking the limit as t approaches 1, then what we're approaching is the natural log of 0, and that's where we have a problem. So the natural log function this right here does not exist, right? This is negative infinity, right? Because we're approaching the natural log of 0. There's a vertical asymptote there. It approaches negative infinity. So that doesn't exist, and this is a divergent integral. Okay. One more thing I'll talk about before I end this video, and you saw this kind of with the other type as well. You might start to predict certain things that happen when you have like a 1 over x, or even if you shift it a little bit, 1 over x to a power. There are patterns, and you can kind of prove them. Maybe I'll make another video actually doing it, but let me just pose the question here. Suppose you wanted the integral from 1 to infinity of 1 over x to some power p dx. And this is a really good question because this gets at something we're going to talk about with infinite series too. There's something called a p series that looks just like this. And it's very much the same kind of question and very much the same kind of answer here. The question is, for what values of p do you think this thing is going to converge, and for what values will it diverge? And you could prove this. We've seen it where, let's put it this way, if p is anything other than 1, you can use the power rule to integrate, right? But when p is 1, then you're going to have to keep in mind that this is a natural log antiderivative, a natural log integral. So you might want to make two cases where p equals 1 and where p does not equal 1. In fact, maybe make three cases where p is 1, where p is less than 1, and where p is greater than 1. And we're mostly interested in positive values of p while I mention it. Like when if p is negative, then it puts the x on top, and then it's less of an interesting question then, right? Because then it gets really big, and then it clearly diverges in that case. Although you could prove it for that as well. But these are the sort of most interesting questions here, I think. So that might be worth exploring. All right. Hope this was helpful, and at some point I may make that third video going through this part.